right, so I'm going to turn on the screen here. So what's going to happen is, so I am recording this now, so I'm going to record all of the C lectures because, you know, nothing makes anyone more self-conscious than having all of their classroom lectures on the freaking internet. So I'm going to do that. As of today, I am hiding everything that's in the Physics C Moodle. I'm just going to hide it all. I would delete it, but, well, I put a lot of effort into that class and I don't want to. So I'm just going to hide it all, and then I'm just going to start adding links of, here's one for electrostatics, here's one for mechanics, or I'm probably just going to leave it as, well, here's what we did. And then just every week have a document with the dates with the YouTube links embedded in there. So this should be up by tonight. If you would like to review it, try not to show it to your parents because it's after school and my filter is gone. All right, so here's the plan. So we're short today. Obviously, we're down to just you two. Down from, let's see, who all are we missing? Brendan, Brian, Jake, Alex, Wes, Mitchell, one or two other people. So we're down quite a few, but that's fine. So what I want to do is I want to finish up what we're going to do with electrostatics for right now. So today's going to be our last day of E&M. We've done as much as we can because circuits, as far as we're concerned, circuits are the same until you get to something called inductors. But you can't get into inductors until you get into magnetism and electromagnetic induction. So don't think we're done with E&M because, dear God, is there a ton more to do. And a ton more calculus to get to. Do you remember I showed you those Gauss's law? Those Maxwell law equations, those 4 of them? We've done one of the 4. We have 3 left. Okay? So we've got plenty more of E&M to do. Now, it's okay. 1 is very, very easy. You never actually use the equation. It just says there's no such thing as magnetic monopoles. So we really only have 2 left to learn. But until we get to magnetism in B, I don't want to teach you it in C, and we still have to go back and do stuff in mechanics. So we're going to take a couple weeks. We're going to go back. We're going to do simple harmonic motion next, which is a brand new thing we haven't even touched in B. But we don't do much with it in B, so we'll just hit it full speed in C. And we talked about it a little bit, yeah, but not a whole ton. And then we're going to go back. We're going to hit torque a little bit harder, and we're going to do angular momentum. We'll come back probably at the end of March, and we'll spend April hammering in the rest of electricity and magnetism. So we'll probably get about 3 weeks of mechanics here, and then we'll hammer in E&M. So we do have to go kind of quickly, but hopefully that will be okay. So I'll talk to you guys. I'll talk to everyone about it tomorrow. But I'm thinking we're going to reschedule the Wednesday morning because I forgot that's going to be NHS. And so, considering I think everyone I just listed that's missing today also is in NHS, including you two. Are you in NHS? I don't know. You okay? It's a sore subject. So yeah, I don't want to again be doing a session if it means no one's going to be here, and I know you have issues with mornings anyway. Not that that's going to change, but we'll probably move that to a Thursday morning, and then again the lectures will be recorded. So if anyone can't make it, great. If you can, all right. Questions?
So like I'm doing mechanics, you had like the modules up. I don't think I finished the last one.
Okay.
Does that matter?
Not really, because let's face it. I think learning C from here's text on the internet was never really gonna work all that well anyway. I can leave it up. Do you remember which module it was? Probably gravitation and oscillation.
I don't know. It might have been 4 and 5.
Okay, I can leave those up and just move them to the bottom. I'm fine with that. Yeah. So I'll just leave them open. I'm not gonna lie. Some of those last modules I kind of dialed in anyway because when I was writing that class, it was hitting the point of, oh, holy crap! I've been doing like 7 straight 12-hour days trying to get this crap done over the summer, and I just want to be finished.
I mean,
so,
we're going to be learning it in here anyways.
Yeah. So let's do 2 more, and then we'll be done with E&M for a while, and then we can focus on mechanics, get some of that stuff taken care of, and then we'll be good. Now, here's the thing. So we are going to be doing this twice a week from now on. We're going to be more involved with this. Here's what this doesn't mean. I got publishers' permission to post a Physics C textbook on Moodle, so that's going to happen this week-ish. Especially like if you know there's one specific test you're taking, like I know you're just taking mechanics. I got a couple people taking just E&M. If you know there's just one test you're taking, I would start reading that freaking thing and start picking stuff up because we're going to do this twice a week. I don't have time to teach you everything. Frankly, in 2 once-a-week sessions, even having taken B, I wouldn't have time if we had started this a month and a half ago. So I'm going to hit the highlights, but I'm hoping, especially in the next couple weeks, this just turns into basically you guys ask questions and I go over it, but it's still going to involve a crap ton of work on your guys' end of learning it on your own. I don't have time to kind of hold your hand through everything. Okay, and I'm not going to lie, there are going to be times you're going to bring me a question, I'm going to go, hey, ask me next time, because I've got to go look it up myself. So, I figure we'll just hit these real quick. There are 2 electrostatics problems in E&M we haven't taken a look at, but again, they should look familiar. So let me kill the lights real quick so we can see this a little bit better. All right, and then really quickly, let me just do this. No, stop that. Just do that. Are you doing anything? There we go. All right. So, what we got here is consider the electric field diagram above. Exciting, right? All right. So here's what they tell us. We've got this electric field diagram with points A, B, C, and D. A, B, and C are all located at a distance of 0.06 meters from the origin, which is this line down here. At which of these 3 points is the magnitude of the electric field the greatest, and justify your answer. So look at it for a second, see if you can come up with it. Yeah, sorry, move if you got to. So what points of the electric field be the greatest?
C.
Why C?
Because it's closest to the lines.
Yep. Straight out from physics B.
Yeah.
C is the closest point to all the lines. It's got the greatest charge density or line density, and so C is going to have the greatest electric field. At which of the 3 points is the electric potential going to be the greatest? You got anything?
This is a B, but there's no reason. I don't have it, but it's just a guess.
Well, remember, when you're talking about electric potential in C, what you've got to talk about is dVdr. Okay? So when you're talking about the electric field, you're talking about your electric potential is the integral of, wait, hold on, do I have that equation right? Yes. So you're talking about the integral. So basically what you're saying is at what point is your sum going to be the greatest? And in this case, it's going to be the same deal. Because these are all the same distance away, C is still going to be your greatest electric potential. B, an electron is released from rest at point B. So what's going to happen in terms of direction, speed, and acceleration? What do you guys think?
It's going to go to the right. Isn't it?
Is it going to go to the right?
I don't know. Yeah, because the arrows are pointing that way.
That's where the arrows are pointing.
Yeah.
Except electric fields always assume a test charge that is
Oh.
positive. And an electron is
Right.
negative. So the electron would go to the left. Now, what's going to happen to the electron as it goes? Because it says in terms of speed, acceleration, direction. So we know it's going to go to the left. And that's kind of a jerky question because, yeah, it's trying to catch you in that. But, okay, so it's going to the left. But what's going to happen acceleration-wise?
The acceleration is going to lower as it gets farther away, but the velocity will continue to increase.
Okay.
Pretty much forever.
Velocity will continue to increase, usually up until some point where basically it's an infinite distance away to some asymptote, but the important thing being that the acceleration is going to continuously decrease. Woo!
Yay.
All right. C, calculate the electron's speed after it has moved through a potential difference of 10 volts. Again, this is straight out, do you remember physics B?
A little bit.
Because we don't care what the electric field's going on. All we care about is that the potential difference is equal to negative W over Q naught. Well, we know our potential difference is 10. We know Q naught is 1.6 times 10 to the negative 19th. And we know that this is equal to work. Well, work is a change in energy, right? So it's equal to 1/2 the mass of an electron, which of course we remember is 1.99 times 10 to the negative 31st.
Of course we do.
V squared. Because in this case, our initial kinetic energy is 0, and so any work done will result in the amount of kinetic energy that we've got. So there, it's just, again, straightforward. Do you remember the equation for B? This could be asked you on a B exam, and it's do the math. The tricky thing being remembering the mass of an electron, but don't forget that's going to be on your constant sheet that you're given both on multiple choice and free response. B and C are separated by a potential difference of 20 volts. Estimate the magnitude of the electric field midway between them and state any assumptions that you made. So if B and C are 20 volts apart, then basically what the assumption you can make is that C is roughly halfway between. So you're talking about your V is 20 and your distance apart is 0.01. And so basically you don't even have to do calculus for this. Again, you can go straight to the B equation of E is equal to V over R, or V over S is how it's sometimes written. So basically your change in potential, your potential difference of 20, divided by your distance of 0.01 is going to give you an electric field of 2,000 newtons per coulomb. Done. And that's just the assumption that you have to make. On the diagram, draw an equipotential line that passes through point D and intersects at least 3 electric field lines. So remember, equipotential is any line where the force at every single point is going to be the same. So you're looking for ones that have about the same density of lines and ones that have about the same direction. So I would say one would be something like that. Every single one crosses the field line at the same angle, and they all have roughly the same density of lines around them. This is actually all B stuff. Not stuff we do all that often because they don't ask it all that often, but it's all B. Ready for the evil stuff?
Yes.
Ready to do actual calculus?
Yeah, let's give it a shot.
Like I said, we'll keep today light because it is just kind of a wrap up from electrostatics. So, this is a fun one. What we got here is a sphere with a non-uniform volume charge density. So before I would always tell you, hey, you've got some uniform charge density, lambda. So then if you had to find the charge enclosed, you would just say, okay, well the charge enclosed is equal to lambda times the volume. And then so you just take lambda times 4/3 pi r cubed, and you're done. Nope. Non-uniform charge density. So inside the sphere, your charge density, your charge as a function of r is equal to rho naught times the quantity 1 minus r over r. Really, I got to come up with some better way of verbally distinguishing the difference between lowercase and capital R. For any lowercase r less than or equal to r. So basically, when you are inside the sphere, your charge is based on that function there. Outside, your charge is Q naught, or is just Q, positive Q. Having fun yet?
Yeah. What's the question that's asked? I might.
Do part A.
Okay. Part A. Determine the following as a function of something for r is greater than r. Magnitude E electric field. Let me get out my notes from before.
It's not a terrible idea.
I didn't have them with me. Which I don't actually think I do.
You you guys get a chance to take a look at anything else off tonight's homework at all? I'm assuming not, since you guys had class.
I have pretty much all of it done from being in class.
What? From what? Like, wait.
The homework we had today in class.
Oh my gosh.
I was just seeing if you guys had a chance to look at anything else or how it went.
I'm having-
For trouble. I can't wrap my head around that. It was just awful.
I got
Yeah.
to teach Morgan. I felt so smart.
Yeah, I couldn't. Still got the wrong answers, by the way.
Okay. Well, if you want to, we can take a couple minutes at the end and we can talk about those.
I'm having trouble with capacitors because I was gone.
Yeah. Well, shocking you were gone.
I was at a college in
Uh-huh.
Tennessee. Far away.
It's true.
Is it asking for the electric field inside or outside?
Well, be careful of the limits, because for A it says, as a function of R, when little r is bigger than, or is larger than big R.
Oh.
So where is it looking for the electric field and electric potential outside?
Inside? Wait, where's R? Where's little r?
Little r is...
Little r is the variable they've chosen, but they're saying little r is bigger than R.
Okay, so it has to be outside.
So we're talking outside of the sphere.
Well, that makes it easier.
Doesn't it? Once you realize that, this should take you about 2 minutes. Not even. This should actually take you about 10 seconds to answer both A and B.
Wow.
Wait. Isn't it just Q? Is that what it's asking, or?
Yeah,
Because it's just, yeah.
that's it.
It's just Q.
Yeah, because if we're outside, what is the total charge enclosed? Q. So you could do delta, or the integral of E dot dA equals charge enclosed
I
over
certainly don't
epsilon
like
naught.
that.
Or you can say, hey, guess what the electric field has to be? Some distance lowercase r away from the center of the sphere when it's outside of the sphere. Done with part A. And again, we could do Gauss's law. We could do that E equals the derivative of dV, or dV over dr. We could do all that crap, or we could just say, by definition, this is the electric field some distance r from a point charge, and this is the electric potential some distance r from a point charge, and be done with it. They will accept either as an answer. Part A is done. So again, and this holds true for mechanics, this holds true for E and M. Don't forget to, first up things above all else, look for what you can simplify down to what you know from B. If you can treat it like a point charge, treat it as a freaking point charge, because then you're done. B, a proton is placed at point P, was shown above, and released. Describe its motion for a long time after it's released. So try and write something down. What's going to happen if you put up a proton at point P and it's released?
It's just going to move away from it.
Yeah, this is the charge outside of it.
Okay, it's going to move away because it's a positive charge and it's a proton. What else is going to happen?
It won't stop.
It what?
It won't stop.
It won't stop. What's going to happen to its acceleration over time?
Decrease.
It's going to decrease.
In the
So this is looking for, it will be moving away, it will continuously speed up, but it will speed up with a decreasing acceleration. That's all it's looking for. So you see how once you kind of see it, A and B should be done in like 30 seconds? What's up?
Yeah.
What do you mean by decreasing acceleration?
By decreasing acceleration, I mean,
Or, you said
Look.
speeding up, but with a decreasing acceleration.
It's
Yes.
just speeding up at a lower rate.
yeah.
Oh.
So it'd be like you slam your foot down on the gas and then you ease up on the gas pedal. Your speed is still going up the whole time, but your speed is going up at a slower rate every second. The better way to think of it, and this is actually a really good example just in general, is think about for gravitational fields. Okay, the escape velocity for the planet Earth is 11 kilometers per second. If you shoot a gun at 11 kilometers per second straight up in the air, that bullet will never return again to the Earth's surface. But every time it's going up in the air, it's slowing down, right? But every time it gets further, so if you go every second, it's traveling slower. But the amount it's traveling slower is slower, if that makes any sense. That first second, maybe you lose 10 meters per second of velocity. The next second, you lose 9.99999 meters per second of velocity. The next second, you lose 9.99998 meters per second. Until a year from then, you're slowing down, but your deceleration or your acceleration is like negative 0.1. And then the next year, it's negative 0.0000001. It's the same thing in reverse. Eventually, you're basically going to essentially reach a velocity of 0, but at that point, the Earth won't be able to pull you back. All right, C. Now we've got an electron of magnitude E is placed at point P, which is a distance r from the center of the sphere, and released. Determine the kinetic energy of the electron as a function of r as it strikes the cloud. So this one's trickier. There are two ways to approach this problem. One that just uses straight out electrostatics. It's an equation I haven't given you, but one that should make sense. And then another one that uses a mechanics approach that we're going to give a shot. That's the work energy theorem. I mentioned it to you guys, but we never actually did anything with it. Here's the easy way. Guys, what is work? It's force times distance, right? Well, what's the equation for force? When we're talking about electrostatics.
Yeah. Oh, wait a second. It is electricity, not electricity, electric
Coulomb's
fields
law?
times.
K, Q1,
Yeah,
Q2, because E is the magnitude of the electron, over r squared. Isn't that force? Times distance. So electric potential is equal to KQE over R. So here's what you can say. You can say that kinetic energy is equal to the loss of potential energy. Right? So you can say that, all right, well, as we strike the cloud, okay. So what we've got here is we're some distance r away here, and this is some distance r. So we can say, all right, so our electric potential out here is equal to KQE over R. But hold on. When we're here, don't we still have kinetic energy that is equal to, or don't we still have potential energy that's equal to KQE over R? Because, I'm sorry, big R and little r is getting ridiculous. So R and R apparently sound less ridiculous to me. Right?
Yes.
So the first is the energy we start with. The second is the energy we still have left when we run into... Yeah. That's the problem. Right now my laptop is transmitting to my desktop, so I'm not technically using my desktop during this whole thing. So it eventually goes to sleep. All right. So what I'm saying here is... Well, how would we find kinetic energy? If this here is our potential energy at point P, and this is our potential energy at the surface, how would we find our kinetic energy? Yeah, you'd subtract them. So let me actually go to, hold on, let me do something. Really? Come on. There we go. All right, so let's go into here real quick, just so I get a little bit more room. And I screwed up everything. Okay. So basically what I'm saying is my kinetic energy is going to be equal to my final potential minus my final initial. So my final potential is KQE over R minus KQE over R. And so basically what I've got is my kinetic energy is going to be equal to KQE times the quantity 1 over R minus 1 over R. And that's going to be my kinetic energy as the electron strikes the surface. And it just comes from that difference in potential energy, right? So I said there was another way we were going to solve it mechanics-wise. This one's more fun. Because do you guys remember the actual definition of work? I mentioned it in the notes before we actually started C stuff.
FD cosine theta.
Yeah, obviously.
FD cosine theta. Nope.
Work here.
Oh, yeah. Duh.
F dot dr, the integral F dot dr. Which is F cosine theta when blah, 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 blah. I'm making certain assumptions. So, what we can do here is say, all right, well, what's the force acting on this thing?
The KQ.
Right, it's KQR.
Yeah, KQ.
KQE
Yeah.
over R.
KQE over R. That's it. QE over R squared.
Right.
Right? Except here's, and then this in terms of dr, except here's the thing. This isn't an indefinite integral, because we care about a specific place, right? We care between point P, which is a distance r away, until we are a distance r away from the center. So we have to take the integral, let me double check I'm putting these in the right places, from R to R. So we get to break out some fundamental theorem of calculus. Woo!
Yippee.
So, again, as with all integrals, I'm just going to pull out all the constants out, because why not? Because it makes life easier. So K, Q, and E are all constants, so let's get them the hell out of there. So we're left with R, 1 over R squared dr. So what's the integral of 1 over R squared dr?
Is
1 over 1/3 R2. Well, that's not right.
that's R to the negative 2, so negative 1/3 to the power of R. No.
Oh, well, okay.
No, negative
Alright, do you
one-
want us to
negative
put it like
R.
R to the
Negative
negative
R.
2?
Yeah, sure. Put it to R to the negative 2.
Negative R, I think. Is that it? I think I did that mental math right. Oh yeah, negative R to the negative 2.
Yeah. Sorry, this should be a negative.
Yeah.
Because remember, we got R squared, and so when we're taking the integral, it's the same thing as if you took the integral of R squared, except
It's the opposite.
it's the opposite. It's completely the same, only different. And that's supposed to be an R, and that's supposed to be capital R, and they both look terrible. All right, and then so from here we get to do some. We get to have some fun with the fundamental theorem of calculus. So remember, the fundamental theorem of the calculus Wow, is you plug in the top and then you subtract the bottom. So I'm just going to leave this stuff over here. I'm just going to put this over here in a little box that I don't care about until I'm done. So what I get is 1. So negative 1 over my top minus negative 1 over my bottom. which gives me, basically, oh, I'm sorry. I screwed some up. This all becomes negative, right? Because that negative gets pulled outside.
Yeah.
Okay, so I get negative 1 over r plus 1 over r. And so I take this whole thing, so work is equal to, well, if I've got a negative here, and I've got this negative here, why don't I just cancel them out? So what I'm left with is k q e 1 over r minus 1 over r, which is the same thing. So yeah, you got to play around with your negatives a little bit, which is a bit of a pain in the butt.
This one's more simple. It requires less work.
This one?
Yeah, I like this one.
You like the fundamental theorem versus the
Yeah,
just definition?
I have a lot of practice with it because of calculus, so this is...
Okay, teach your own.
No,
I
I suck
know.
at calculus. I like the other one.
You suck at calculus and you're taking the physics C test.
Yeah,
Good.
well, I'm
Lord.
trying. I'm,
Oh, why did I open?
well, yeah, I'm
that?
taking mechanics. So.
All right. Yeah, you'll be
I'm
fine.
working on it.
You'll be fine. You'll be fine. All right. Well, 2 more parts, I think, and then we're done. 2 more parts. And frankly, I'm just really only going to bother with part E, or part D, and then I'll just show you part E, and then we'll get going, because it's getting a little bit late, and frankly, once we've done Gauss's law one time, you can do it another 15 times, who cares? It's just an exercise in algebra. The fun part is this expression for P naught, or rho naught.
It shows all of the R's for this. Every one of them.
So, what do we do?
I don't have the expression. Okay, well...
Let's start with what we know. And what do we know about rho naught?
If you multiply it by that, it gives you that.
You multiply it by that, it gives you that. What's that and what's that?
1 minus R over R gives you R, PR.
Okay, we do know this expression here, right?
Yes.
We know that expression. All right, so let's try that. So what we've got is, hold on 1 second. Okay. So, what we know is the charge function is rho naught 1 minus, what was it? R over R?
Yeah.
You know, as helpful as that is. Lowercase r over capital R. Right? Now, if only we had some point where we knew what the charge was, right? Because then couldn't we work backwards from there?
Yes.
Well, isn't it Q? It's like,
The whole thing equals Q, right?
yeah.
So can I do this? Can I say the charge is Q if you were to add up the entire charge over the entire volume of the sphere?
Okay. Yeah.
So if I sum up the entire sphere, it's got to add up to Q.
Yes.
So let's do that. So let's go ahead and do the integral, although, hold on, there's a problem. What is it? Q's a constant, that's not a problem. Rho naught's a constant, that's not a problem. Big R's a constant, that's not a problem. But what are we integrating in terms of?
Volume.
Volume.
Oh.
What's our variable?
Or,
Radius.
Right.
We can't take an integral, we can't do that.
like,
Whoops.
You're integrating in terms of v with a variable of r. That doesn't work.
Right.
Well, at least not yet. So what do we do?
well,
You guys are the ones in calculus, taking a lot more recently than me. What's the solution?
you use it, plug in pi or Q. Is that it? Isn't that volume of a sphere?
Right there. That would work.
I don't think it's quite pi or cubed.
Is it? No, whatever.
No.
4/3 higher cubed, I think, is what.
Which one?
Well, that is volume, but remember, we don't want volume. We want a substitution for volume. But can't we find volume by saying, well, volume is that. Because surface area is just for any small given amount of r, right? And if you sum up all of those dr's, you get volume.
Right.
I mean, if you think about it, the integral of 4/3 pi r squared in terms of r is 4/3 pi r cubed, right?
Yes.
This is our solution that lets us get this done.
Okay.
Because now we've got a volume, but it's still in terms of dr. The problem is if we just replaced, we can replace v with 4/3 pi r cubed. We can't replace dv, because dv is some infinitesimal slice of v, and that's why we have to do surface area. Make sense?
We missed your.
All right, so we say q equals the closed integral from 0 to r, rho naught, 1 minus r, 4 pi r squared dr. Well, what's the trick I always say I want to do?
Pull the rest of it.
Get any constants out. Just get rid of them.
So wouldn't that be all pretty much like the rho naught from the 4 pi r squared?
The 4 pi is, but the r squared, that's a lowercase r. So we can pull out the big R if we really felt like it. I'm not going to bother to at this point. But so what we are left with is, so we got, come on, Q is equal to 4 pi rho naught, the integral from 0 to r. So I had 1 minus little r over big R, right? The whole thing times r squared. So I need to distribute that r squared through. So what I get is r squared minus r cubed over r dr. So give it a shot real quick. See if you can get the integral done.
I think I have it.
Wait, are we putting in the big R for the little r's?
We will. We will.
Yeah.
I just left
Not
it.
yet, no. But we will. Because that's going to be our fundamental theorem of calculus. The top minus the bottom.
I have r cubed, which is over 3, minus r to the power 4 over 4r. 4 big R.
What's up, Morgan?
I wrote it wrong, but it's fine. Why doesn't the little r get distributed to the big R as well?
Because the big R.
What do you mean?
The big R is on the bottom, so.
So you don't distribute it?
Well, because remember, this was 1 minus r over r.
Mm-hmm.
So that's the same as saying, like, 1 over big R times r.
Oh.
Right? Which, if you
Yeah.
multiply that by r squared, is 1 over big R, r cubed.
Okay.
That's why. So it is, but
Okay.
Yeah,
It just doesn't affect the bottom or just
yeah, because it's multiplication, it only affects the numerator in this case.
Right.
All right, so what you should get is r cubed over 3 minus r to the 4th over 4 big R. And this is all between 0 and big R. So then you go ahead and you do the fundamental theorem of calculus, which means you take the entire function times the top, or with the top plugged in for little r, minus the entire function times, or with the bottom plugged in. Well, look, what's the bottom going to be?
0.
It's 0. So it's 0 cubed over 3, which is 0, minus 0 to the 4th over 4r, which is 0, and the whole thing times 0 is 0. So we don't even have to worry about that. All we have to say is, all right, well, what this means is q is equal to 4 pi rho naught big R cubed over 3 minus big R cubed over 4.
Yeah, that's
No. Because of course this is going to be r to the fourth over 4r, which cancels out to r cubed over 4. Now, this whole thing asked us for, however, rho naught. Right? That's all it cared about. So at this point, well, let's solve everything for rho naught. By the way, what's r cubed over 3 minus r cubed over 4 going to be?
negative. No, just. Would you have to make the values the same?
Yeah, sure. So
So it's 1
this could be 7 twelfths.
r cubed over 12.
Hold on, where did that go?
That's what I got. Because the 4 to the top, to the left one, and the 3 to the
Oh yeah. This 4 would cancel. Good call.
Oh, I didn't do that. But
That 4 would basically cancel. So what you're left with is q over pi rho naught, multiply the 3 over. Oh, I'm sorry. I don't want the p naught rho naught there. I'm solving for freaking. Let's try that one more time. So I'm going to divide over the pi. I'm going to multiply over the 3, and I'm going to divide over the r cubed. And so what I'm left with is rho naught is equal to 3q over pi r cubed. Okay? Now, very briefly, by very briefly I mean in 30 seconds. Part E said find the electric field inside the conductor, or inside the sphere, right? Very briefly, Gauss's law, yes? So what you would say is, okay, well, E dot dA same thing it always is. E dot dA, they're going to be parallel, so you can drop the dot, and it's just going to be the surface area of the sphere, and blah, 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 blah. For the Q enclosed, though, it's a little trickier, because we know that it's the function is rho r, right? So the charge enclosed is going to be rho r. I'm sorry, that should still be rho r times v. That's going to equal q. So what you'd have to do is say, okay, well, E 4 pi r squared is equal to, well, you take that function, which is rho naught, which we just found was 3q over pi big R cubed, times 1 minus little r over big R over epsilon naught. And from here, you could solve for the electric field. But at this point, it's just an exercise in algebra. So I'm going to leave that to you guys. Okay? What I can tell you is this. If I go to, let's see, what year is this? 2003, I think. So for part E, what you should get is KQR, lowercase r over capital R cubed times the quantity 4 minus 3r over r, which all comes from this whole ungodly mess here that I'm not about to even attempt. Okay, because it's just, again, algebra and who cares. We got the idea? Any questions? All right, so we kind of hit through electrostatics a little bit quickly. So I'm giving you homework. By Thursday, I'm going to post these up on Moodle. But so there's this guy. I've recommended his videos before, but he gives a really good overview. So what I would like is if sometime between now and Thursday, because like I said, we're going to go into simple harmonic motion. So I'm going to go into it, assuming you've watched Kinematics of Simple Harmonic Motion, Part 1, 2, 3. Okay. All told, it's about half an hour. You can kind of skip through, like, if you understand what's going on, you can skip through a lot of stuff because he does get a little long-winded. I'm going to post the link to this and then just say watch the first 3 videos. So if we can make sure we got that done by, say, I think we're going to plan on Thursday. Is there anything big going on Thursday that I know of? Okay. So I'm just going to assume we know this, so I'm going to post this link, this video. I'm going to post the go to this link to watch these other videos, and then we'll pick it up on Thursday. Sound good? All right.
Thursday before school or after?
Thursday before school.
Okay.
I've got